Good morning student, this is our fourth lecture on electrostatics and today's topic of discussion is very important to build up the entire concept as far as electrostatic is concerned, and that is electric lines of forces. So as far as Michael Faraday, have you heard the name of Michael Faraday? So Michael Faraday, somewhere between 1791 he is born and he died on 1867. So during this period of time, Michael Faraday, he had introduced the concept of lines of forces. Why he had introduced the concept of lines of forces? Just to visualize both electric field as well as magnetic field. So to visualize the nature of electric and a magnetic field, Michael Faraday introduced the concept of lines of forces. But you remember very well that the existence of or lines of forces do not have any physical existence. They are only the imaginary things. They are only the geometrical construction. So according to Michael Faraday, both electric field as well as magnetic field, they are made up of what? Lines of forces. As we know that in case of a magnetic field, suppose we are having a bar magnet. Surrounding to bar magnet, there is a presence of magnetic field, and that magnetic field, it is made up of magnetic lines of forces. These magnetic lines of forces, they originate from North Pole and they will come to end on South Pole. Magnetic lines of forces, they originate from what? North Pole, and they will come to end on a South Pole. Pole strength of North Pole is plus Qm, pole strength of South Pole is minus Qm. So as far as the magnetic dipole is concerned, from the North Pole, magnetic lines of forces, they will emerge out, and at the South Pole, magnetic lines of forces, they will come to end. Similarly, if I just consider that here there is a presence of an electric field, you know very well that both positive as well as negative charges. If we are having a positive charge, it will produce its own electric field to its surrounding. If we are having a negative charge, then again surrounding to that negative charge, there is a spherical region where that charge produces its own electric field. So whether the charge is positive or negative, both will produce the spherical region to their surrounding, where that Coulombian force is experienced by a test positive charge, and that region is called an electric field. So according to Michael Faraday, as a magnetic field is made up of magnetic lines of forces, so electric field is also made up of what? Electric lines of forces. So let us see that electric field is made up of electric lines of forces. Then how these electric lines of forces are produced? Suppose here that this is a region of electric field which is non-uniform electric field. Suppose we are having what? Non-uniform electric field. Non-uniform means intensity of electric field at different points are different. Intensity of electric field, their magnitude as well as their directions are different. So in the region of non-uniform electric field, suppose we are having the different points P, Q, R, S, T, U, V, where I had shown the intensity of electric field as E1, E2, E3, E4, E5 like that, E4, E5, E6, E7. And what you can say, as I had represented electric field intensity by means of an arrow, see there, lengths are different as well as the directions are different at different point. It means electric field intensity, their magnitude is different as the length of arrow is different. Their direction is different as the direction of arrow is what? Different. Means intensity of electric field at different point in the region of non-uniform electric field, both magnitude as well as the direction of electric field intensity are different. You know, by definition, electric intensity or electric field intensity is nothing but force experienced per unit charge. Means force experienced by a test positive charge, it is directly proportional to intensity of electric field at that point. So, in the region of non-uniform electric field, let us consider that a test positive charge Q0 somewhere from infinity, we may brought it at point P. As soon as that test positive charge Q0 is kept at some point P in the region of electric field, what is the force acting on that charge? Force acting, see here, intensity at this point is E1, test positive charge is Q0, so the force acting on a test positive charge when it is kept at point P is F1 equal to Q0 into E1. Means this force F1 is directly proportional to what? Intensity E1. And what happens to the charge? When a force is applied to a charge, that charge undergoes displacement, and that displacement of charge is directly proportional to what? The amount of force. Greater is the force, greater will be the displacement. Smaller is the force, smaller is the displacement. So, that charge moves from point P to Q due to force F1. As soon as it reaches the point Q, again Q is a point in the region of electric field, means there must be certain electric intensity, and electric field intensity at point Q is E2. Means again that charge is acted upon by some another force F2 which is equal to Q0 into E2. That force F2 is directly proportional to what? E2. And depending upon the magnitude of force, that charge undergoes displacement x2 which is directly proportional to F2, and that F2 is directly proportional to what? E2. So that charge will move like this and it may reaches, that charge undergoes displacement x2 and reaches point R. At point R, because R is a point in the region of electric field, so there is certain electric intensity. So the electric field intensity at point R is E3. So that charge is once again acted upon by what? Force F3 which is equal to Q0 into E3. This force will displaces the charge through a displacement x3 which is proportional to F3, and F3 is proportional to what? E3. Means as soon as charge reaches the point R, it undergoes a further displacement x3 and reaches a point S. At S again it is acted upon by force F4 because intensity at point S is what? E4, and it reaches this point, means that charge will continuously move from one point to other point depending upon what is the intensity of electric field at different point in the region of non-uniform electric field. So see what happens to the test positive charge. When test positive charge is brought somewhere from infinity to some point P in the region of non-uniform electric field, then as soon as charge is brought at some point, it is acted upon by certain force. That charge will move along the direction of force, and after traveling a displacement which is proportional to force acting on it, again it reaches some point, some other point in the region of electric field where once again it is acted upon by force, means that charge will never be stationary. It is continuously moving from one point to other point randomly. See here, how is the direction in which that charge is moving? It is moving randomly from one place to that of what? Other place. So, the path along which, so this is a path along which a test positive charge will move in the region of an electric field. That imaginary path traced by a unique positive charge in the region of electric field is called as lines of force of electric field, or it is also known as electric lines of force. So what is electric lines of force? It is a path along which a test positive charge will move in the region of an electric field is called electric lines of force. Or let us consider that I want to find out what is the direction of electric intensity at some point R. We know that this is the curve or the path along which that test positive charge is moving, and we are calling it as an electric line of force. So electric line of force, it is an imaginary curve. It is what? It is an imaginary curve drawn in the region of electric field such that a tangent drawn at, this is a tangent drawn at any point on the given curve, a tangent drawn at any point. Here I had drawn the tangent at point R. So a tangent drawn at any point on the curve will use the direction of electric field intensity at that point. So a line of force, electric line of force. So electric lines of force can also be defined as what? The imaginary curves drawn in the region of electric field such that these imaginary curves are drawn in such a manner that a tangent drawn at any point on the curve, a tangent drawn at any point on the curve will give us the direction of electric field intensity at that point. Or electric line of force, it is the path along which test positive charge will move in the region of electric field. The path along which a test positive charge will move in the region of an electric field is called electric line of force. Now, we will see the different characteristics or properties of electric lines of forces. Now you have some idea regarding electric lines of forces. Why the concept of electric lines of force was introduced by Faraday? Faraday introduced the concept of electric lines of forces just to visualize electric field or just to visualize magnetic field. To visualize the nature of electric field, concept of lines of force was introduced. And now you must remember, what is electric line of force? It is a path along which test charge, unit positive charge called as test charge, the path along which test charge will move in the region of electric field is called electric line of force, or it is the imaginary curve drawn in such a manner that a tangent drawn at any point on that curve. Suppose this is electric line of force. If a tangent is drawn at any point on that curve will give us the direction of electric field intensity at that point. Remember that as far as the strength of electric field intensity is concerned. Suppose we are given the region of electric field which consists of what? Electric lines of forces. So many electric lines of forces are there, you cannot count them. And you were given a task that find the electric field intensity, strength of electric field intensity at some point P in the region of electric field. What is the task given to you? Measure the strength of electric field intensity at any point P in the region of electric field. What we have to do? Draw a unit area round that given point and count the number of electric lines of forces which are passing normally through that unit area in one particular direction. What do you mean by number of electric lines of forces passing normally through unit area? Number of electric lines of forces passing normally through given area is called electric flux. And if they are passing normally, it is the normal electric flux. So flux per unit area is nothing but intensity, because we know that vector E dot vector ds is equal to electric flux phi. Vector E dot vector ds is equal to electric flux phi. So remember that intensity of electric field, it is directly proportional to what? Electric flux. Means the density of electric lines of force, density of electric lines of force will decide or will indicate the strength of electric field at that point. The density of electric lines of force will decide the strength of electric field at that point. Means if electric lines of forces, they are close to each other. So for example, just here we may have a situation like this. Now if I draw the area like this, if I count the number of electric lines of forces which are passing through a unit area drawn round a given point. Here lines of forces, they are close. Here lines of forces are what? Widely separated. Means the density of electric lines of forces in this region is more, whereas density of electric lines of forces in this region, it is somewhat less. So the strength of electric field in this region where the lines of forces, their density is more, strength of electric field is more, whereas the region where lines of forces are widely separated, the strength of electric field in that region is what? Weak or less. So you just underline one thing, that the strength of electric field will depends on density of electric lines of forces. It will depends on what? Density of electric lines of forces. Now we will see one by one the characteristics of electric lines of forces. So the very first and important characteristics of electric line of force is that no two electric lines of forces should ever intersect with each other. See what I am saying? Electric lines of forces do not intersect each other, they do not meet each other. Why it is so? Suppose I will say that this is the first electric line of force and this is second electric line of force, and they are meeting at point P. Let us consider the situation when the two lines of forces, they are intersecting each other. Remember, as far as electrostatic is concerned, it has its own basic laws, and as per the basic rules of electrostatic, electric field, intensity of electric field or electric field intensity at a given point will have a unique direction. Means in the region of electric field intensity has one and only one direction. Now here we had considered the situation where the two electric lines of forces, they are intersecting each other. When I consider that P is a point of intersection P, it may be a point on first line of force or second line of force. When P is considered as a point on the first electric line of force, here that first line of force is traveling along this direction. Means this is the path of progress of that electric line of force. So by definition, to find out the direction of electric field intensity at point P, let us draw a tangent. A tangent drawn at any point on the curve, tangent drawn at any point on electric line of force at a given point will give the direction of electric field intensity at that point. So the direction of electric field intensity at point P is along E1 when P is a point on first curve, but P is a point of intersection, means P is a point on second curve also. So when we consider that point of intersection is a point on second line of force and that second line of force is advancing like this. So to find out the direction of electric intensity, let us draw a tangent at point P. Then the direction of electric field intensity will be along the tangent drawn along the direction of electric line of force. So what we will see here, at a given point we are having what? Two different directions of electric field intensity, which will violate the basic rule, because at any point electric field intensity must have a unique direction. So in order that electric field intensity at any point in the region of electric field will have a unique direction, no two lines of forces, they were allowed to intersect each other, or electric lines of forces, they neither meet each other, they do not intersect each other. This is one of the important characteristics of properties of electric lines of force. Now the second important property about the electric line of force, that suppose we are having a positively charged object and a negatively charged object. We are having two objects. One of the object is given positive charge, other object is having what? Negative charges. Then the electric lines of forces, these positive charges, they produces their what? Own electric field. And what happens to the, suppose this is a test positive charge. When a positive charge, test positive charge, it is kept in the region of electric field, it starts moving from one place to other place randomly. So the positive charges which are deposited on the surface of that object, they will live. They start moving in the region of electric field. But near to this positively charged object, we are having what? Negatively charged object also. So these positively charged object, from the positively charged object, when positive charge starts moving, it may enter the region of what? It may enter the region of electric field produced by the negative charges deposited on some other object. What happens? That positive charge, it gets attracted and it will combine with negative charge. So there is annihilation of positive and negative charge. Where there is annihilation, there is an annihilation of positive and negative charges on the surface of what? Negatively charged conductor. So what happens here? That when the two objects, one of them is positively charged, other is at negative charge. When they are kept near to each other, each object because they are charged, they produces their own electric field. And when positive charge on positively charged object starts moving in the region of electric field produced by them, and as soon as they enter the region of electric field produced by what? Negatively charged object, suddenly they get attracted by the negative charges which are deposited on that object, and when positive and negative charge they come in contact, they will destroy, they will vanish, or there is an annihilation of charge. So what conclusion we can draw? See here, this is the path along which positive charge is, this is the path along which that electric charge is traveling. The imaginary path along which test positive charge will travel in the region of electric field is called electric lines of force. Means here there is a formation of what? Electric lines of force. From where that electric lines of force will originate? Electric lines of force will originate from positively charged object, and they will terminate on the surface of negatively charged object. So electric lines of force originate from the surface of positively charged object, and it will come to end on a negatively charged object. Now there is one more characteristics. Suppose that these are the conductors. These are the conductor. One of them is positively charged and other is what? Negatively charged. Remember, the positive charges which are deposited on a conductor, these positive charges, remember, charges will be deposited only on the surface of conductor, not in the interior part of conductor. So these positive charges on the surface of conductor, they produces their own electric field. This is the electric field produced by positive charges on a conductor. Whereas this is the electric field produced by the negative charges which are deposited on the surface of conductor. We know that the positive charges on the surface of conductor, as soon as this electric field is produced, these positive charges do not remain stationary, they start moving in the region of electric field. And during their motion, when they enter the region of electric field produced by negative charges, they get attracted towards the surface of what? Negatively charged conductor. But the basic difference here is that when positive charges leaves, when they will leave the surface of conductor, they leave the surface of conductor at what? At right angle. Lifting of positive charge particle from the surface of conductor is what? Normal. Once they leave the surface of conductor normally, they may travel along any path, but during their motion, when positive charge comes near to the surface of negatively charged conductor, we know that a strong force of attraction will be acted upon by that negatively charged conductor, and that positively charged conductor suddenly it recombines with a negative charge and both get vanish. So due to strong force of attraction, they will terminate again at right angles. So see here, when positively and negatively charged conductors they brought near to each other, positive charges on conductor will leave the surface of conductor normally, as well as they will terminate themselves normally on the surface of what? Negatively charged conductor. So electric lines of forces starts from positively charged conductor and they will terminate on negatively charged conductor normally. How is the origination of electric lines of force? Electric lines of force originate Where they will originate? Electric lines of force will originate from what? Positively charged conductor. They will terminate. Terminate means finish. So they will terminate on negatively charged conductor, and at both the surfaces that electric line of force is normal. So there is a normal origination as well as termination of electric lines of force from positively charged conductor and negatively charged conductor. So you can remember one of the characteristics that electric lines of force originates from positively charged conductor and they will terminate on negatively charged conductor normally. That word is what? Normally. That normally word is important. Now, let us see whether the electric lines of force can pass through a conductor or not. Suppose we are having an electric line of force, means that positive charge is traveling along this path. Positive charge is traveling along a path, because what is electric line of force? It is a path along which test positive charge is traveling. And in the path of electric line of force, suppose we are having a conductor. We are having what? A conductor. What is the electric field intensity inside the conductor? Electric field intensity inside the conductor is 0. It means F by Q0 equal to 0. Therefore, what is the force acting on charge inside the conductor? Force acting on charge inside the conductor is 0. Means, is there any movement of charge through a conductor? No. So what we can draw a conclusion? That electric lines of force do not pass through a conductor as electric field intensity inside the conductor is 0. As electric field intensity inside the conductor is 0. Or one may have a classical explanation that because this is a conductor, it carries free electrons in it, and when positive charge strike with free electron, they get recombined and vanishes. Means electric line of force will come to end when they reaches the surface of conductor. So remember, anyway, you remember one of the important characteristics of electric lines of force, that electric lines of force can never pass through a conductor as electric field inside the conductor is always 0. Electric field inside the conductor is what? 0. Now, there is one more characteristics, that is regarding intensity of electric field. If this is a region of electric field, this is a region of what? An electric field, and we want to find out what is the strength of electric field at any point P. The strength of electric field at any point P in the region of electric field. What we will do? We will count the number of electric lines of forces which are passing normally through a unit area drawn round that point, and that will give us the strength of electric field. More the lines of forces passing normally through a unit area drawn round a given point, greater will be the strength of electric field at that point. So if I have some surface area, say dA, to which that electric field intensity is normal, then the electric field intensity, strength of electric field intensity at any point is equal to number of electric lines of forces which are passing normally through a unit area drawn around that point. In short, you remember the definition of electric field intensity. How you can define electric field intensity? Number of electric lines of forces passing normally through a unit area drawn around a given point will give us the strength of electric field at that point. Strength of electric field at that point. Now, because you are measuring the strength of electric field in terms of number of electric lines of forces passing through what? A unit area. If lines of forces, electric lines of forces, they are crowded. Suppose we are having this situation, there is a point Q where I will draw a unit area and here is a point P. And let us see the situation. We want to find out the electric field intensity at point P and at point Q. P is that point surrounding to point P. If I draw a unit area and if I count the number of electric lines of forces which are passing normally through that unit area in one direction, then they are found to be what? Very large. Means the strength of electric field at point P is strong, whereas Q is a point surrounding to which if a unit area is drawn, very few electric lines of forces they are passing normally. So I can draw the, and therefore the strength of electric field at point Q, it is found to be weak. So two conclusions can be drawn and they are the characteristics or properties of electric lines of forces. What is that first property? That the region where the strength of electric field is strong, electric lines of forces are crowded. The region where the strength of electric field is strong, electric lines of forces they are what? Crowded. And the region where the strength of electric field is weak, electric lines of forces they are what? Widely separated. So see, on a single concept you can write the three basic properties of electric lines of forces. Definition of electric field intensity, number of electric lines of forces passing normally through a unit area drawn round a given point is called intensity of electric field at that point. The region where the strength of electric field is strong, electric lines of forces are crowded. The region where the strength of electric field is weak, electric lines of forces are what? Widely separated. Now, in case of non-uniform electric field, we had seen that charge is moving randomly from one point to other point. Now let us consider that we are having the presence of uniform electric field. What do you mean by a uniform electric field? If the magnitude as well as what? The direction of electric field intensity at every point is same, then that electric field is called uniform electric field. What is uniform electric field? The electric field in which both the magnitude as well as the direction of electric field intensity will be same at all the points, then that region is called uniform electric field. Means if I say that P, Q, R, S or A, B, C, D, E, these are any points in the region of electric field, then both the magnitude as well as direction of electric field at every point it should be same. Means I can represent the electric field at different points. See here, electric field at all the points, their magnitude is same as well as their direction is same. So that's why they are represented by means of an arrow of same length and pointing in what? Same direction. So in such a uniform electric field, see here, if a test positive charge is brought somewhere from infinity to a point P, I may bring a test positive charge from infinity to some point P. What happens to that test positive charge? You know that electric field intensity by definition E must be equal to F divided by Q0, means force exerted on test positive charge in the region of electric field is Q0 into E, means force exerted on test positive charge is directly proportional to what? Electric field intensity at that point. But electric field intensity at every point in uniform electric field is same. Their magnitude is same, their direction is same. So, as soon as that test positive charge will be kept at point P, it is acted upon by a force F is equal to Q0 into E. And what this force will do? That force will displaces the charge. And the displacement of charge is directly proportional to force experienced by test positive charge. So that charge will move from point P and will reaches a point Q. Q is a point in the region of what? Uniform electric field. What is the electric field at point Q? Same as that of electric field at point P. Means that charge will be acted upon by same force. Means that charge will undergo same displacement. So it moves from point P, Q, and it reaches a point R. Again, R is a point in the region of electric field. Electric intensity at point R is same. Means again that charge Q0 is acted upon by same force F. So that charge once again undergoes same displacement from R and it will reaches S. So this is the path along which that test positive charge will move. I can bring the test positive charge somewhere at this point. So in this case also it will move along this path. And what you can say that this is the path along which test positive charge is moving whenever they are kept in what? Uniform electric field. Or this is the path along which test positive charge will move whenever they are kept in what? Uniform electric field. And how is this path? It is a straight line. So electric lines of forces, they are what? Straight lines. Electric lines of forces, their path or they are what? Straight lines in the region of uniform electric field, and they are parallel to each other also. Spacing between them is same, they do not intersect. So in the region of uniform electric field, electric lines of forces, they are straight line and they are also parallel to each other. They are also what? Parallel to each other. Now we will just summarize the properties of electric lines of forces, but before that, in examination there might be a question, because here according to concept of electric lines of force, suppose I will have a positive charge and a negative charge. Both positive as well as negative charge, they will produce their own electric field, because that spherical region surrounding to charge in which Coulombian force is experienced by a test positive charge is called the region of electric field. And according to concept of lines of force introduced by Michael Faraday, that electric field is made up of electric lines of forces. So remember, the electric lines of forces or the electric field produced by a positive charge consists of electric lines of forces. And how is these electric lines of forces? They are acting along the radius and directed outward. Means a positive charge produces radially outward electric lines of forces. So whenever you are having a positive charge, it will produces an electric field to its surrounding, and that electric field is made up of electric lines of forces which are radially outward in nature. But if we are having a negative charge, no doubt it will also produces its own electric field. That electric field is also made up of electric lines of forces. But here the electric lines of forces, no doubt they are radial, means they will act along the radius, but their direction is towards the negative charge. Means you can say that the electric field produced by A negative charge consists of electric lines of forces which are radially inward in nature. Which are what? Radially inward in nature. Now suppose we are having the two opposite charges. One is plus q and other is minus q. So here this is plus q, here this is what? A minus q charge. Both the charge will produce their electric field as per this instruction. So this positive charge produces electric lines of forces and negative charge will produce electric lines of forces which are pointing what? Inward. Whereas the electric lines of forces produced by positive charge is what? Radially outward. And these electric lines of forces, so here electric lines of force starts from positive charge and they will come to end on what? A negative charge. So whenever you are having two unlike charges, one is positive charge, other is negative charge, then from the positive charge you can show the lines of forces moving away, and at negative charge you can show lines of forces that are approaching towards the negative charge. Now you may have a situation both the charges are positive, plus q, or both the charges are negative, minus q, minus q. Positive charge means here you can show the electric lines of forces in this manner. Why it is so? It is because no two electric lines of forces they are allowed to intersect. So both the positive charges will produce the electric lines of forces and they will travel in this manner, that at the most they remains parallel but they should never intersect. Whereas as far as the negative charges are concerned, in case of negative charges, same is the situation, that the electric lines of forces they will come to end on negative charge, but they are not allowed to intersect with each other. So when we are having two positive charges or two negative charges, electric lines of forces can be drawn in this manner. But remember, electric lines of forces will never allow to intersect. So that's why at the most you can show that these lines of forces they are what? Parallel to each other. Lines of forces are parallel to each other. Again, to show that electric lines of force do not pass through a conductor because electric field inside the conductor is zero. So if I draw the electric lines of forces, if these are the electric lines of forces, then remember electric lines of forces they do not pass through conductor as electric field inside the conductor is zero. Or if we are having a situation, suppose that these are the electric lines of forces, already I had shown it. So if these are the electric lines of forces and they are pointing outward in this manner, and if I just draw a unit area surrounding to point A, here lines of forces passing through that unit area in one particular direction is more because the density of electric lines of force is more. Whereas if I just consider any point B around which I had drawn a unit area, number of lines of forces passing through unit area they are less. Lines of forces are widely separated. So what conclusion you can draw? That the strength of electric field at point A will be more because strength of electric lines of force is more, or more lines of forces will pass through a unit area drawn around point A, whereas the strength of electric field at point B is less because the number of electric lines of forces passing through unit area drawn around that point B they are less. So as less lines of forces are passing through unit area around the point B, therefore the strength of electric field at point B is weak. So these are some pictorial representation as far as electric lines of forces are concerned. So student, you must remember one thing, that electric lines of force do not have any physical existence. It is just the imagination made by Michael Faraday. Why? To visualize the presence of electric field, presence of magnetic field. So he had introduced this concept of geometrical construction just to study the nature of electric field and the nature of what? Magnetic field. Nature of electric field and nature of magnetic field. So here there is one more another important concept, that is of electric flux. Already we know that the strength of electric field intensity, it is defined as number of electric lines of forces passing through a unit area in a given direction. So number of lines of forces per unit area, number of electric lines of forces per unit area is nothing but strength of electric field, that is electric field intensity is equal to number of electric lines of forces divided by area enclosing those electric lines of forces. Number of electric lines of forces, which is also known as what? Electric flux, upon area enclosing those lines of forces will give us the strength of electric field or electric field intensity. So remember here, electric flux phi E, phi suffix E, flux is denoted by phi and the suffix E will represent electric flux. Remember, to distinguish between magnetic flux and electric flux, magnetic flux is denoted by what? Phi suffix B, electric flux is denoted by what? Phi suffix E, E stands for electric field. So what is the definition of electric flux? Electric flux, it is always calculated over a given area. So electric flux over a given area is nothing but number of electric lines of forces which are passing normally through that area in one particular direction. Number of lines of forces passing through a given area is called electric flux over that area. So the electric flux phi E, it can be written as, see here, E multiplied by area, E into area. So suppose we are having a situation like this where electric lines of forces, they were passing normally through some surface area S. So S is the surface area, total surface area through which some electric lines of forces are passing normally, and we want to count what is the electric flux over that total surface area. Flux over a surface area S is equal to E into what? Area. See here, situation is like this, that surface area, remember surface area up till now for you area is a scalar, but remember surface area, it is a vector. If I say that this is the surface area of some irregular shaped body, we may be given irregular shaped body whose surface area is S. I can consider that surface S is made up of so many small surfaces, 1, 2, 3, 4 like that, and when I want to calculate the total surface area, then that total surface area, it can be obtained by integrating the small surface area ds. So here surface area S is not along the direction of electric field intensity. Here surface area S, it makes an angle theta with the direction of electric field intensity. Remember what I am saying? That surface area is a vector which is always normal to the given area. If this is the area ds, then the surface area ds, it is represented by means of an arrow which is normal to that area ds. So surface area is a vector, And in case if that vector is not, that area is not normal to E, area S is not parallel to the direction of electric field. Surface area S is not in the direction of what? Electric field. It is at some angle theta. Then what is the component of area along the direction of electric field? Component of area along the direction of electric field, it is ds cos theta, because you know that any vector, it can be resolved into what? Two component. That component which makes an angle theta, already in the topic of scalar and vector, we had seen that any vector, when it is resolved into two rectangular component, then the component along x-axis, it is a cos theta, because that component makes an angle theta with given vector. So as S makes an angle theta with E, so the component of S along the direction of E is ds cos of theta. So electric flux is equal to E into that component of area, which is along the direction of what? Electric field, that is ds cos of theta. This is one way. Or one may calculate the component of E, which is normal to the surface area. Component of E, which is normal to what? The surface area. So remember, the electric flux phi E is equal to electric field intensity E multiplied by that component of area which is along the direction of electric field, that is ds cos of theta. And you know that vector E dot of vector ds, because ds is area vector. So E dot ds is equal to E into ds into cos of theta, by definition of what? Scalar product. Therefore electric flux phi E d phi E, electric flux d phi E is equal to vector E dot of vector ds, because we can replace E ds cos theta by what? Vector E dot of vector ds. So d phi is equal to vector E dot of vector ds. Now this is the small flux associated with small surface area ds. Out of total surface area S, here we had calculated what is the flux associated with small surface area ds, and that flux associated with small surface area ds, it is d phi E equal to E into ds. Now the total surface area can be calculated just by taking integration. So integration of d phi E is equal to phi suffix E equal to integration of vector E dot of vector ds, or it is equal to integration of E ds cos of theta. E ds cos of theta, or d phi equal to phi equal to integral of E ds equal to E ds cos of theta, or simply you can write this is E cos of theta into integration of ds, or it may be equal to what? E s cos of theta, because integration of ds is equal to s, or it may be vector E dot of vector s. Phi is equal to vector E dot of vector s. Phi is equal to what? Vector E dot of vector s. So let us revise whatever we had seen, that is what is electric field, electric lines of forces, their properties, and that of what? Electric flux. So one by one we will revise it. So let us just revise in short what we had studied in our today's lecture. First, the definition of electric line of force. What is electric line of force? It is an imaginary curve. It is an imaginary curve drawn in the region of electric field in such a manner, in such a way that a tangent drawn at any point to that curve will gives you the direction of electric field at that point. An imaginary curve drawn in the region of electric field such that tangent drawn at any point on that curve will gives you the direction of electric field at that point. That is known as electric line of force. Also, we had seen that when test positive charge is brought in the region of non-uniform electric field, what happens to that charge? It starts moving randomly from one place to other place and tracing a certain random path. So, the imaginary path along which a test positive charge or a unit positive charge moves in the region of electric field is known as electric line of force. What is electric line of force? It is the path along which a unit positive charge moves in the region of electric field is called electric line of force. Now, the different characteristics or properties of electric lines of forces. The very first and the important property that the electric line of force, it always originates from a positively charged object and it will terminate, means come to end on a negatively charged object. Electric lines of force always originate from positively charged object and it will terminate or come to end on a negatively charged object. This is the first characteristic. Second one, the electric lines of forces, they will never intersect each other. They are not allowed to meet each other, because in case if electric lines of forces they are intersecting, it means that at their point of intersection electric field is found to have two directions, which is against the basic laws, because according to rules, according to basic laws, that electric field intensity has a unique direction at every point. So to obey that law, it is essential that no two electric lines of forces should ever allow to intersect each other. The third property, which is same as that of first one, that the electric lines of force leave or terminate the surface of conductor normally, means from positively charged conductor, from where that line of force will start, it is always normal to the surface of positively charged conductor, or the surface of conductor to where that electric lines of force will terminate. Again, at that point also, it is normal to the surface of what? Negatively charged conductor. So remember that the electric lines of forces leave or terminate on a conductor normally. Leave or terminate to a conductor what? Normally. Now the fourth point, that is regarding what? The characteristics or properties of electric line of force, that the lines of force do not pass through conductor. Why they do not pass through conductor? Because line of force means a unit positive charge is traveling along certain path, and in its path, if there is a conductor, what conductor consists of? Large number of free electrons. When line of force reaches the conductor, that free or unit positive charge, it recombines with free electron and they will vanish. In other words, you can say electric lines of force, they do not pass through conductor. Electric lines of force, they do not pass through conductor, that is electric field inside the conductor is zero. Electric field inside the conductor is zero. The magnitude of, next property, the magnitude of electric field intensity, that is strength of electric field, it is proportional to number of lines of forces per unit area. Number of lines of forces per unit area of the surface held perpendicular to the field. Sixth one, the electric lines of forces. If the lines of forces are crowded in some region, then the strength of electric field in that region is what? Large. If the electric lines of forces, they are widely separated, then the strength of electric field in that region is what? Weak. And as far as uniform electric field is concerned, lines of forces are straight line, they are parallel to each other as well as what? They are equispaced. So this is all about the characteristics or properties of lines of forces. Again, you remember two more definition, that whenever we will talk about electric flux, remember flux is denoted by a sign phi, and phi suffix e, it means it is electric flux, and it will represent electric flux is calculated over a given area, and electric flux is nothing but number of electric lines of forces which are passing through a given surface area, or number of electric lines of forces enclosed by a given area is called electric flux over that area. Similarly, to find out the strength of electric field intensity or intensity of electric field, it is simply flux per unit area, means the number of electric lines of forces per unit area is called intensity of electric field. So this is the most important part of electrostatic to build up the basic concepts in electrostatics.